Okay, so let's talk for a minute. Just a reminder that we have our exam on, I'll distribute that on Thursday, okay? And then you'll have through Monday to work on that thing. I will post one lecture so that we just kind of keep rolling on that, but we won't meet in class on Thursday or Friday, but we will be back Monday, okay? So just to remind you of that. And again, Maria asked before class whether you could use your notes. The answer to that question is no, but remember I am giving you access to this, right? So I'm giving you access to this thing right here. Oops, there's an error. Okay. Let me close all these. Where is it? I think it's down here somewhere. Series tests. So this is what I'm giving you access to, which is basically the combination of things I put on the slides. At the end, I think it was in 9.6 or something like that, that I actually put all of these things together, okay? And some of these things are more restrictive than they need to be. For instance, where is the limit comparison test down here? It says the terms need to be positive. No, they don't, okay? Terms don't need to be positive. There were some other ones that were slightly too restrictive. Let's see, where were they? Well, this one right here, the geometric series, we actually know a more general version of this, right? This one, demands that the powers start at 0. Okay, so it's like, it would be like A plus AR plus AR squared. But we know better than that. We don't have to do that. So yeah, this is what I will give you access to when you're taking the exam. So when you take the exam, just make sure you're not doing anything other than just looking at the test itself. This will be the last page of the test, yeah? So that's kind of a good barometer of whether or not you are currently cheating, okay? If you're just looking at the test, you can't do that, okay? And I would ask that once you start the test, that you not go back and look through your notes. Does that make sense? So once you start the test, the clock starts and you're not allowed to like say, oh man, there was an example that he did, good grief. And then Sunday morning before church, you go and look at that example, right? And then after church, you feel guilty and then you email me and tell me you cheated. Okay. So just don't look at your notes once the clock is started over the weekend, okay? But you will have access to this, which is a good thing. Okay? All right, any questions on that? Okay. Today it's the next section is a little strange, okay? We're going to start, and I'm going to kind of share this. I'm just going to write some stuff on the whiteboard version of this thing, okay? So here's what we're going to be doing. In 10.2, what's really happening is we are talking about things that are potentially not functions, okay? We're going to talk about something called parametric equations, okay? Now, there's a word in here that I want to hone in on. It's parameter. So parametric equations have to do with a parameter. And essentially the big idea is to turn non-functions into functions, okay? And when I say non-functions, I mean of what I really mean is of two variables, or actually of one variable, sorry. Need to erase this. On functions of one variable into functions. Now, it's not like I can just magically make something that fails to be a function of one variable into a function of one variable, okay? That's not what's going on here. What you do is you actually introduce another variable that kind of helps you to that end, okay, into functions. And this is going to happen by introducing an additional variable. A parameter. Okay? So that is kind of what's happening here. Okay? So let's look at an example, shall we? Just to kind of see what it is we're talking about here. Now, what about the unit circle? Okay, the unit circle looks like this. Okay? And what is built on the back of the unit circle? What area of mathematics, a huge, giant area of mathematics, is built on the back of the unit circle? Trigonometry, all of it, all of it. Every bit of it is entrenched right here in this one shape, yeah? So don't discount the importance of the unit circle. Now, now we just finished doing stuff with conic sections. A circle is a conic section, yes? Okay? And remember, we had that general form for an ellipse that was like x minus h quantity squared over a squared, where a was the distance to the, along the major axis over to one of the vertices, yeah? And then it was plus y minus k squared over b squared, where b was the distance from the center up to one of the points on the minor axis, yeah, equals 1. But we said if this is a circle, a and b are equal, yeah, and it's just the radius. Okay, and in this case, the center is the point, is the origin, 0, 0, yeah? So what is the equation of this thing? What is the equation of the unit circle? X squared plus y squared equals 1. It would be basically x minus 0 squared over 1 squared plus y minus 0 squared over 1 squared equals 1, which is really just x squared plus y squared equals 1. Now, part of the problem with this is this equation on its own, is not a function of x. You understand what I'm saying? And it's not a function of y either. So that's what I mean by up here at the beginning. We're trying to turn non-functions of one variable into functions by introducing a new variable that we call a parameter, okay? Now, why is it not a function? Do you guys remember what the definition of a function is? Yeah, it has to pass the vertical line test, which basically means any x input, we know where it goes. It has to go to one point, yeah? Any x input that we put in our domain has exactly one y input, yeah? And therefore, we could say that y is equal to something in terms of x. That's what it means to be a function of x. So each input has a unique output. And that is not true here. Each input in x actually has 2 outputs, yeah? And that's problematic. So what we would do to kind of try to fix that is we might just focus on like the upper semicircle or something. And the equation of this thing would be y equal to, help me out here, that would be y equal to what? If I just did the upper part. The square root of I mean, I have this equation right here, yeah? Y is equal to the positive square root of 1 minus x squared. But the problem is that only takes the upper part, yeah? The lower part, okay, which is this stuff right here. Okay, how would I describe that part of the unit circle? Y equal to what? Negative the square root of 1 minus x squared. Yeah, so it'd be the negative square root. So I have the positive square root and the negative square root. The problem is to really fully understand what's happening with this thing, I would really need two separate functions. Does that make sense? So the goal is, so what's the goal that we have? The goal is to describe this with one function. Okay? And what is the solution to that end? Well, we introduce another variable called a parameter. And this probably isn't going to be all that surprising to you. Basically how we do that, okay, so here's the solution right here. Here's the solution. We let x equal, now remember, when we were doing trigonometry, the x coordinate was given by something. What was the x coordinate given by? Oh, right. So we flipped a coin there. It had to be one or the other, right? Cosine, okay? X equal to cosine of t, all right? And y, so look, x and y each become a function of a new variable. Does that make sense? And so what's y going to be? Sine of t. Okay, and this guy right here, this t thing, this is called our parameter. Okay, so we've introduced a new variable that actually does make us a function, but it's a function of what? It's not a function of x or a function of y. What we have here is a couple of functions of, yeah, so note, let's just make a little note right here. X and y are functions of t, this new parameter. And what we have to do when we do this is we always have to talk about what the range of the parameter is, okay? So like for a given t value, why is it that these are functions? Well, you give me a t value, I know what the x coordinate is now. And it's going to put me at a certain place on the unit circle, yes? It's like if t is equal to 90 degrees, for instance, pi over 2, where am I? T is equal to pi over 2, 90 degrees. That means I'm up at the point 0, 1. Does that make sense? Yeah? But to get the entire unit circle, to get the entire thing, what should I let t go between? No. T. X and y will go between -1 and 1, yes. But that will happen by letting t go between 0 and 360 degrees, yes? So 0 less than or equal to t. And really, we don't even need to go all the way up to 2 pi, 360 degrees. We can, because we already encountered that point at 0. So in other words, let's talk about where we are. So I am right here when t is equal to 0. Do you know what I'm saying? Yeah? Where am I when t is equal to pi over 4? Well, I'm right here. Okay. So this is where I am when t is pi over 4. Okay. Right here is where I am when t is equal to what? Pi over 2. Okay, I'm actually down here when t is equal to 3 pi over 2, for instance. Here, I'm right here if t is equal to pi. But the whole point is, I know exactly what the output is. The output is now like a point X and Y, right? So let me just kind of point out here that the output, so T is the input, okay? And the output is X comma Y. Okay, it's actually an ordered pair. Does that make sense? Okay, so the output, you know, if T is equal to pi over 2, for instance, the output is like X cosine of pi over 2 is 0, sine of pi over 2 is 1, so the output is 0 comma 1, yeah? Right, that's like the output of that point right there. So T equal to pi over 2 produces the output point 0 comma 1, yeah? And sometimes it's helpful, you know, so like this thing is a function of T, yes? For each input, I have a unique output, right? I understand that we still have the problem of this thing kind of wrapping underneath itself, yeah? But I know exactly where I am for each particular T value. One thing that we're inclined to do when we set up, you know, a parameter like this is we describe the direction that we traverse this curve for increasing values of T. Okay, so which way are we traversing this curve for increasing values of T? Counterclockwise, right? So what we do is we can kind of draw, like, and this will become more and more important when we get into physical applications, okay? This right here is called the orientation of the curve that's been parametrized, okay? So in the end, this right here is called a parametrized curve, okay? Is this making sense? We are turning a non-function into a function by introducing a parameter, and we're watching what happens as we move around this curve, yeah? That will help us to be able to do calculus very effectively on these curves, okay? We'll differentiate with respect to T, for instance, now, yeah? We'll be able to tell exactly what's happening with these curves as we parametrize them. Any questions on that? That's one example. And by the way, notice, like if somebody handed me this as the parametrization, right? Oftentimes this is referred to as a parametrization. Okay, that's a big word, right? Parametrization. If somebody hands me a parametrization, sometimes I want to go in the reverse direction and express this thing in terms of X and Y, yeah? So I mean, if I take this thing, I can actually eliminate T by saying, well, for crying out loud, like X squared plus Y squared, that's like cosine squared T plus sine squared of T. But what's cosine squared of T plus sine squared of T? Always 1. So I can recover the XY equation that describes this thing. Does that make sense? This is called, this is a technique called eliminating the parameter. So sometimes someone will hand you an already parametrized curve, and you will want to kind of recover the XY version of the equation that we're dealing with, okay? Parametric equations, okay? So cosine T, sine T. Hey, what about any circle? Okay, so let's actually, you know, let's do another example here. What about any circle? Any circle, okay? X minus H squared plus Y minus K squared equals R squared. What do you think about that? Okay, so here, I don't know, here's H, here's K, here's the center, and I have a circle of radius, what? R, yeah? What do you guys think? What are we gonna do in this case? How would we parametrize this curve? Because this is not a function either, is it? Right, it's fairly badly behaved. So it seems like the introduction of a parameter might be in order here. Well, here's one tip. Why don't we just write this as x minus h over r quantity squared plus y minus k over r quantity squared equals what? Right, that's equal to 1, yeah? So it's like, looks like thing squared plus thing squared equals 1. Yeah, Daniel.
So, like for example, with eliminating the parameter, you set x squared plus y squared equal to cosine squared t plus sine squared t.
Right, so I set, in the unit circle case, I set x equal to cosine of t. The thing that was being squared, I set equal to cosine of t. And that did the job of moving me around the unit circle. Yeah?
So set x minus h over r.
Yes. If you set that equal to cosine of t, and if you set y minus k over r equal to sine of t, and what do you think I would let t run between, Daniel?
Wouldn't it just be the same?
Yeah. Okay, so you kind of shift everything and think of it as the unit circle, but then what is really happening with this? Let's kind of rewrite this. X is really, what's x really equal to? If I multiply through by r and I add h, so it's going to be h plus r cosine of t, and y is equal to h, oh, oops, not h, what is it? K plus r sine of t. And this is for 0 equal to or less than t less than 2 pi. There it is. This is our parametrization. Parameterization. Okay? And let's make sure that this thing is actually working. If I plug in t equal to 0, where am I? Think about it. What's cosine of 0? 1. What's sine of 0? 0. So at t equal to 0, what is x? At t equal to 0, what is x? So I mean, like, look, you can almost make a little table. Do you know what I'm saying? So you can make, so t, x, y. Do you know what I'm saying? If t is 0, what is x? H plus r. Exactly. And what is y? Okay. So where am I? I'm right here. Right? This is where I am when I'm at t equal to 0. This is the point h plus r, after all. Yeah? Think about it, right? Because this point right here is h plus the radius. And I am k pi. Yes? Where am I at t equal to pi over 2? Well, what's cosine of pi over 2? 0. So x is h. Okay? And what's y? Yeah, k plus r, exactly right. Amazing. So I am right here if t is pi over 2, right? I am at the point h, comma, k plus r. And now do you see what's happening? It's just moving us around the circle again in the way we did around the unit circle, yes? Except this time it's any circle at all. So cosine and sine were just what the doctor ordered. In which way are we traversing this thing for increasing values of t? It's always, the orientation is determined by increasing values of t. So I start at 0, I start increasing t, and I traverse this thing in the counterclockwise direction. Okay? Boom, 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 boom. Yeah? Does that make sense? What about any ellipse? What do you think would be going on with that? What about any ellipse? Okay, what's the equation of an ellipse? X minus h squared over a squared plus y minus k squared over b squared equals 1. And just to kind of get you thinking in the right direction, because this seemed to kind of get people thinking rightly before, why not write this as x minus h over a squared plus y minus k over b squared equals 1. What do you think the parametrization is going to be this time? So let me just draw a picture here. Okay, here is h, here is k. Okay, let's see. Oh boy, something like that, right? So here's my foci or whatever, right? Okay, that's not a very good picture of an ellipse, but I think you get the gist of what's happening here. There's my center, I have the foci. Apparently my vertices are these guys right here because this time it looks like I have a horizontal major axis. What do you think the parametrization should be this time around? Any suggestions? What do you think would move me around on that curve? What has the property that thing squared plus thing squared is 1 all the time? There's really only one thing that fits the bill. Sine and cosine. So what do you think I should do? X minus h over a is going to be cosine of t. By the way, here's the little secret to keep in mind. I don't have to set this equal to cosine. I could have set it equal to sine, but it would just be sort of confusing. Does that make sense? It would just move me around the circle in a different way, okay? So I could actually mix things up if I want. The main thing is I want functions such that if I add the sum of their squares, I always get 1. And what else does that other than sine and cosine, yeah? Okay, so that's equal to cosine of t. And then I say y minus k over b is equal to sine of t. So in other words, x is going to be h plus a cosine of t, and y is going to be k plus b sine of t. So the a and the b properly distort the x and the y coordinates so as to like put this on an ellipse rather than just a circle. Does that make sense? Before, sine and cosine were scaled by the radius, and that just kind of scaled out the unit circle to a circle of radius r. Now having different scaling numbers, a and b, is going to like scale me out in the x direction and the y direction properly to keep me on this ellipse. And what's t going to go between? What do you guys think? 0, 2 pi. 0 equal to or less than t less than 2 pi. Exactly. Exactly right. There is my parametrization. And now let's think about this. Where am I? Remember, this distance right here is A. And this distance right here, all the way, you know, from here up to here, that's B. Does that make sense? Okay. Okay, so where am I when t is 0? Where am I when t is 0? Yeah, this is where we are. If t is 0, I'm at the point h plus a, comma, k. Where am I at t equal to pi over 2? Cosine is 0 at pi over 2, yes? Sine is 1 at pi over 2, so it's going to be h comma k plus b. Okay, that's where I am at t equal to pi over 2. That is the point h comma k plus b. Do you see what is happening? How are we traversing this ellipse? What's the orientation? Counterclockwise. We're going like this. Okay, counterclockwise around this thing. So that parameter t will move me around the ellipse in that counterclockwise direction. Okay? Is this making sense? How do you suppose? Well, I'll leave it at that. We'll talk about sort of hyperbola stuff later on, but I want to talk about some other things for our own sake, other than just the conics, because it turns out you can do parametric equations for things other than just the conics. Turns out there's going to be a way that we can actually parametrize a hyperbola, for instance, yes? And we can even parametrize like both sides of a hyperbola kind of simultaneously with one parameter, which seems kind of weird. Like the function is going to jump from one side to the other somehow. Like what is going on, right? But there's some interesting ways that you can pull that off, okay? All right, so I said that sometimes you want to go in the reverse direction. So someone gives you a parametrization, and it's up to you to actually figure out what the curve looks like. Does that make sense? Okay. And actually, let's go ahead and do that. Okay. So here's an example. So this time we're going to start with the parametrization. Okay. So x equals 1 plus 1 over t, okay, and y equals t minus 1, okay? So the question is, what is this parametrized curve? Okay. So clearly, since no parameter was, or so like no domain for the parameter was specified, I'm just going to take the biggest domain possible. Okay. So what's the only thing I would not be allowed to plug into this? 0. So we would just say t just can't be 0. Okay. What is this parametrized curve? And I just want to illustrate that. Actually, here, I'll kind of share this. Okay. We'll go into Desmos here. I'm going to get rid of this thing. How do I do this? Hide floating median controls. Yes. Okay, so what I want to do is go into Desmos. And I'm pretty sure that you can just say x equals, what was it? It was 1 plus what? 1 over t. And then y equals, I think, or maybe this is, maybe I have to go like this. X equals this and y equals, what was it, t minus 1 or something? This was working earlier. Why is it not working right now? Maybe I have to go like this. Maybe if I go like this, without the y equals thing. Yeah, here we go. Okay, do you see how, look at how this, do you see that little point kind of moving around right now? Do you see that? Yeah? You see it's kind of tracing out a curve. Do you see that? Okay, it's interesting. I'm kind of sliding this thing around so that way we can kind of see stuff happening here. But what we want to do is actually eliminate the parameters. So let me kind of write on the screen here for us. And I'll erase this once I'm done. So we have x equal to 1 plus 1 over t, and I have y equal to t minus 1. The goal is to kind of eliminate the parameter. What in the world is happening? Why isn't this thing? Hang on a second. Am I sharing the screen? Just want to make sure I'm sharing this thing. What is going on? Return to meeting. Okay, yes. Okay. I am sharing my screen. Okay. So why is this thing not allowing me to annotate on the screen? Of annotators it should be writing. I'm writing on here and you guys aren't seeing it for some reason. That's sort of weird. Okay. Well, I'm going to actually go in here then and kind of share this then. Okay. So let's do this. So x equals 1 plus 1 over t. Y equals t minus 1, correct? All right. So let me ask you, if I want to eliminate the parameter, how do we eliminate t? What would you do? How would you eliminate t and kind of figure out what this thing really is? Yeah.
I guess I would try to figure out what t was in terms of x.
Okay. Or in terms of y.
Yeah.
You might figure out what t is in terms of x and y, and then eliminate it from the other thing. So do you see an obvious way to solve for t in terms of x or y? Yeah. T is equal to y plus 1 always. And then you're going to take this guy and do what with it? Right. So you get x equal to 1 plus 1 over y plus 1. And up here, of course, we had t different from 0. Yeah. But that's the same thing as saying, I mean, think about it. T different from 0. That's the same thing as, now look at this equation. X is equal to 1 plus 1 over y plus 1. In this equation, we better not have y be what? Y had better not be equal to what? Negative 1. But do you guys see that that's exactly what would happen if t was 0? Do you see what I'm saying? Yeah? So these two things actually correspond to one another, right? These two conditions that are sitting right here, okay? Okay, so x equal to 1 plus 1 over y plus 1 is apparently the equation that we're dealing with here, yes? And incidentally, you could kind of algebraically shift some things around and end up with y being a function of x, yes? Okay, let's actually go back over into Desmos and watch that thing kind of play out over there. Okay, so here we go. Okay, so we had that. What was the other curve? What did we come up with? It was x equal to what? 1 plus 1 over y plus 1. So there it is. Do you see that? So watch what happens. I can let the t parameter kind of move around. Do you see how it's moving us on this curve right now? That's kind of cool. Yeah? I think that's a pretty neat little thing, right? You can kind of see that the parametrization is moving us along on this thing. Okay, so how does it move us for increasing values of t? That's something that we want to know. So watch. If I let t increase, watch the point kind of come into the screen. For increasing values of t, do you see where it's moving us? It kind of moves us in an up and left direction along the lower branch first, yes? And where does it hop from the lower branch to the upper branch? What's that? So if I'm on the lower branch now, yes? When is it that we hop from the lower branch to the upper branch? What's going on here? Yeah, once t is, and that kind of makes sense because think about it. X would have to be greater than 1, wouldn't it? If t is negative, think about it for a second. If t is negative, then it's going to be like 1 plus something negative. So it's going to be less, x is going to be less than 1. Do you see what I mean? But then once t is positive, we get an x value that's bigger than 1. And therefore, we would have to be on that right branch. Because you can kind of see right now I think you can, right? So like if I x equal to 1, you guys see that that's kind of like an asymptote for this thing, yes? X can never be equal to 1. Why? Because 1 over y plus 1 is never going to be 0, okay? All right, so let's see here. Once we kind of jump past 0, also like if we think about y is equal to t minus 1, correct? Okay, and it looks like y equal to, see, where is that other kind of asymptote happening? Y equal to minus 1 or something, do you see that? Yeah? There's kind of a horizontal asymptote at y equal to minus 1, vertical asymptote at x equal to 1. When is it that the y value kind of jumps from being below minus 1 to above minus 1? Well, once t goes from being below 0 to above 0, because like the y coordinate is t minus 1. You see what I'm saying? If t is below 0, we're going to be below minus 1, or we're going to be below minus 1. If t is above 0, we're going to be above minus 1. Yes? So at t equal to 0, we make this transition from the lower branch to the upper branch, the lower left branch to the upper branch. Okay, so let's kind of watch that occur. Oops, what am I doing here? This is silly, right? X should be 1, okay? Let's let t move around. Okay, so t is increasing. You kind of go up and to the left on the lower branch. Then at 0, we transition to the upper right branch. And it looks like we go kind of up and to the left again. Does that make sense? We're kind of moving up and to the left all the time. Up and to the left is the orientation of this thing for increasing values of t. Okay? Does that kind of make sense? Yeah? So there we kind of went in the reverse direction. Someone handed us a parametrization, and from that we extracted an equation in terms of x and y, and sorted out what that curve actually looks like. Okay? Any questions? Any questions on that? Cool. Not really sure why this thing is not allowing me to annotate on the screen. What? What is going on here? Okay. Now all of a sudden it's allowing me to, so like if I were going to draw the orientation, it would be like this, correct? Kind of goes like this for a while, and then what happens later? Goes in this direction. And this part of the curve happens for t less than 0, and this part of the curve happens for t greater than 0. Does that make sense? Yeah, those were the two things that we kind of discovered there. All right, we're going to be working exclusively with parametrizations for the coming lectures and doing calculus with some of these parametrizations. Okay? That's it.